Hello, welcome to another module in this massive open online course. So, we are looking at convex optimization problems. We have looked at the canonical or the standard form of a convex optimization problem. In this module, let us look at an important subclass of convex optimization problems, which is basically linear or the class of linear programs. Okay, so what we want to look at is basically linear programs, which are also referred to as LPs, and this forms it's a subclass, as I already said. It's you can think of this as a special case or a type of convex optimization problem, or a subclass of of convex optimization problems. Okay, and now a linear program, okay, and this is also referred to as, can also refer to this as an LP, as I already said. It's a linear program is also an LP, and well, linear program can be expressed as follows. That is, remember, any optimization problem has an objective. So it's minimize A bar transpose x bar plus B, okay, which basically has a linear objective or an affine objective function subject to the constraints which are also affine, that is C bar transpose Ci bar transpose x bar less than or equal to di for I equals 1 2 up to L, and equality constraints which have to be affine in any case for a convex optimization problem, as we have seen in the previous module. That is C tilde J transpose x bar equals D tilde J for J equals 1 2 up to n. Alright. So, basically the constraints, the equality as well as the inequality constraints. Alright. So, all affine, that is, it has affine equality and slash or inequality, affine constraints and slash or inequality constraints. So, basically linear objective. Now, of course, an affine function is a convex function. So, the objective function is convex. Alright. So, and an affine object, there is an affine constraint, is also convex. So, therefore, this is a special class of convex optimization problem. So, a linear program is a subclass of convex optimization problems in which the objective function as well as the constraints, equality as well as inequality constraints, are all affine in nature. Alright, and you can say this is, so this is basically your linear program. And well, you can say this is the simplest because everything is affine. This is the simplest class or category of convex optimization problems. Now, just for convenience, I can write this in matrix form. So, I can represent the LP in matrix form as follows. It's not very difficult. So, I have minimized the objective, which is A bar transpose x bar plus b, subject to the constraints. Now, constraints I can represent them as a matrix. So, I can write this as C1 bar transpose, C2 bar transpose, CL bar transpose x bar. Now, this is component wise, that is each component of the vector on the left has to be less than each component of the vector on the right. So, this is a component wise, is also, remember, is also termed as component wise. This is the component wise inequality. So, I can write this now as your matrix C times x bar component wise less than, this is your vector d bar. Alright. So, I can represent it in a compact form using matrices. Similarly, the equality constraints I can represent them as C1 tilde transpose, C2 tilde transpose, Cm tilde transpose times x bar equals d1 tilde up to dm tilde. So, this becomes your C tilde x bar equals d tilde. Okay. And therefore, the compact, this can be written in compact form as follows: minimize A bar transpose x bar plus b subject to C x bar component wise less than d bar and C tilde x bar equals d tilde. So, this is a, you can say, a compact form for a this is the compact form for the linear program. Okay. So, this is basically expresses your linear program in a very compact form, using vectors and matrices. Okay. Let us look at an example for this linear program, and we have already seen this before, that is, we have already introduced this before. That is the example of base station cooperation, where there are several base stations in a cellular communication scenario, where there is a user at the edge of several cells, or the intersection or the region that can be served by several cells, all right, or can be served by several base stations. So, the different base stations, typically when the user is at the edge of a cell or at the edge of cells, the user can be served by several base stations belonging to the different cells which are overlapping at that particular point. And so, we consider a scenario in which this particular user is being served by several base stations, or not just a single user, in fact several users can be served when the by different base stations cooperating with each other. All right. So, let us take a look at our example of base station cooperation or cooperative and we have already seen what happens in base station cooperation. In base station cooperation, we have a group of cells that are cooperating to transmit to one or many users. So, I have different users and the base stations are transmitting to the various users in a cooperative fashion. Normally we have a single base station serving any particular user, but in this particular this particular scenario, base stations can cooperate to serve the various users, thereby enhance the SNR, enhance the reliability of communication in a wireless communication scenario or a wireless cellular communication scenario. Alright, so this is basically your base station. So we will consider a scenario in which we have k So we have k base stations and m. So k base stations are cooperating in this cooperative cellular scenario to serve basically m users. Okay, and in this scenario, let Pij would denote the power of power transmitted by base station I to user j. Okay, and we will denote by Hij is the feeding channel coefficient. So magnitude Hij square equals Gij represents the power gain between base station I and user j. Okay. So Pij denotes the power transmitted by base station I to user j, alright, and magnitude Hij is the feeding channel coefficient, magnitude Hij square, which is Gij, represents the power, the gain from base station I to user j. Okay. And therefore, now if you look at the power that is received by each user I, so the power that is received by each user I in this cooperative fashion is the power, sum of the powers that is transmitted by all the base stations. So I have I equals 1 to k Pi1 Gi1. This basically is the power received at user 1. This is the power received at or this is the power that is basically the sum of the powers, correct, that is the sum of the powers received from all the base stations, alright. And remember, we said this has to be greater than or equal to P1 tilde, which is the minimum power desired by user 1. This is the minimum power desired by user 1. So, the sum of the powers received from all base stations has to be greater than or equal to P1 tilde. This has to also hold similarly for the other users. So, at user 2 we must have the sum of the powers received from all base stations, that is Pi2 Gi2 summation over I equals 1 to k over all base stations, that has to be greater than or equal to P2 tilde, and so on and so forth, that is summation I equal to 1 to k Pim at user m, summation I equal to 1 to k Pim Gim greater than or equal to Pm tilde. Okay, so these are your constraints. Okay, and you can see these are basically affine constraints. and now we need an objective. One of the objectives that one can consider is basically we want to meet the desired power level at each user, but simultaneously we also want to transmit the minimum amount of power. So, what is the total, what is the minimum total power that can be transmitted by all base stations to all users to meet these desired criteria at the various users. So, the objective function can be to minimize the total power transmitted by all the base stations to all the users. So, now that makes it a convex optimization problem. So, the objective function can be minimize summation I equal to 1 to k, summation j equal to 1 to summation over all base stations, summation over all users Pij, that is power transmitted by the base stations to all. So, this is your linear objective. Remember, it is simply the sum, so therefore, it is a linear objective. Linear objective, and this represents, remember, this is the total power by all base stations to all users. Alright, this is the total power by all base stations to all users. So, what is our optimization problem? Our optimization problem is to minimize the total power transmit power of all the base stations to all the users subject to these constraints, that is the power received at each user is greater than a minimum threshold, which is denoted by Pj tilde. Alright, at user 1 it is P1 tilde, user 2 P2 tilde, so on at user m it is Pm tilde. And you can clearly see the objective is linear, constraints are linear, this is a linear program. So, this is cooperative base station transmission or base station cooperation. This is basically, this is a, one can formulate a base linear program, and you can see thus the variety or the interesting and very interesting applications of the simple yet very flexible and powerful optimization framework of that of a linear program. So, this can be obtained to minimize the total transmit power, total power that has to be transmitted by all the base stations to all the users. Now, also note that in the standard form convex optimization problem, the inequalities have to be less than or equal to. So, and one can readily convert it to the standard form by simply introducing a minus sign. So, I will have a minus in front of everything, and the inequalities become less than or equal to. So, this becomes minus is less than or equal to, and this is now your standard form linear program. So, this is your LP to simply minimize total transmit power of base stations to all the users. Okay. Now, an interesting variation on this problem can be the following thing. Now, if you look at the transmit power of any single base station, now let us look at the transmit power of base station I, that will be equal, that can be represented as P of I. So, the transmit power of base station I can be represented as P of Pi equals summation, that is the power transmitted to all the users, summation over all users Pi j. Okay. For instance, P1 power transmitted by base station 1 equals j equals 1 to m P I or P1 j, that is the power transmitted by base station 1 to each user j summed over all the users. Okay. So, this is power transmitted by total transmit power of base station 1, in fact, that is what this is. Okay. And now, what we want to do is we want to consider an interesting optimization objective function in which we want to minimize the maximum of the powers transmitted by the various base stations. So, the total k base stations. So, you have transmit powers Pk. So, you want to minimize the maximum. So, what this is doing is minimizing the maximum power transmitted. Minimize the maximum power transmitted by base station. Now, what happens typically in this cooperative cellular scenario is that there are several base stations, and when you minimize the total power transmitted by all the base stations together, that might result in an undue burden on a single base station. All right. So, one particular base station which probably has good channel conditions, or where the channels to the different users are good, can be overburdened or overtaxed in comparison to. So, this does not ensure that the load is. So, the previous total power minimization does not ensure that the power is uniform, that the power load, that is the burden, the transmit power burden is not uniformly levied on all the base stations. All right, there might be different base stations which are levied more, or which have to transmit more power in comparison to others. But when you are minimizing the maximum transmit power, what this does is that this ensures a sort of fairness in the power burden. It sort of ensures that this power burden for the different users is rather fairly distributed on all the base stations. So, this is an important property of such problems. So, this ensures, you can say, the minimax criterion basically ensures fairness in the power burden, power burden or the power distribution, minimizes the maximum power, and subject to the constraints are there as usual. That is, if you look at the desired power at each user, that has to be greater than the threshold. So, the constraints are there. So, this is now, if you look at this minimax, now if you look at each pi, okay, and we already seen this, each pi is summation j equals 1 to m, is summation j equals 1 to m p1 j, and this you can see this is affine, okay, or this is convex. Okay. So, each of these P1, P2, Pk, each of these powers so each of these is convex, all right, and therefore, when you take the maximum of this, remember the maximum of a set of finite or infinite convex function is convex, all right, and therefore, the maximum of this set is convex. So, this implies the maximum of this is convex, and therefore, this is basically convex, and therefore, you are minimizing a convex optimization, convex objective function. Constraints are as usual, I mean similar to the previous one, they are convex. So, this is also a convex optimization problem, okay, and this is also therefore convex optimization problem. Now, what is its relation to a linear program? Now, at present it seems unrelated to a linear program, but we are going to demonstrate that this is in fact can be written as an equivalent linear program, and for that we will use the epigraph trick that we have seen in the previous module. So, how can this be written as a linear program? So, we have minimize. Now, we will use the epigraph form. So, I can write this as minimize t subject to the objective maximum of P1, P2, Pk, this is less than equal to t, and the rest of the constraints are as usual there, that is summation I equal to 1 to k Pi1 greater than or equal to P1 tilde, and so on and so forth, summation I equal to 1 to k Pim greater than or equal to Pm tilde. Now, the maximum of P1, P2 up to Pk less than or equal to t, the maximum of a set of quantities is less than or equal to t if and only if each of these is less than or equal to t. So, this implies each has to be each p, this implies each pi has to be less than or equal to t, and now I can write the equivalent optimization problem. Therefore, this is optimization problem is equivalent to minimize t subject to, now we need that each pi is less than or equal to t. So, this means P1 equals summation 1 j equals 1 to m P1 j less than or equal to t, j equals 1 to m P2 j summation less than or equal to t. This is the power transmitted by base station 2 to all users, and finally summation j equals 1 to m Pkj less than or equal to t. These are the base station power constraints, and you have the user constraints as well, similar to previous. So, summation I equal to 1 to k Pi1 greater than or equal to P1 tilde summation I equal to 1 to k P I m greater than or equal to Pm tilde. I am sorry, this has to be I am missing here missing the channel gains. The channel gains are very much there. So, this has to be Gi1 Gim greater than or equal to P1 tilde Pm tilde, and similarly this has to be Pi1 Gi1 so on and forth summation Pim Gim greater than or equal to Pm tilde. Similarly here also, and summation I equal to 1 to k Pim Gim greater than or equal to Pm tilde. Just let me make sure that we are not missing this at any point. Yes, in fact I think that, so we want to minimize the maximum, correct. Using the epigraph form, I can write this as minimize t such that the maximum is less than or equal to t. The desired power at each user has to be greater than or equal to Pj tilde, that is there as usual, and if the maximum is less than t, then we have each Pi is less than t, which implies that. So, I can write this as, so now we have this as basically the k constraints and you can see each is an affine constraint, okay, and this are your previous m constraints. So, the minimax optimization problem has k this has a total of k plus m constraints, all right. So, this has a total of, so this is, so you can write the minimax. So, this is also an LP. So, you can see each of these, all these constraints are affine. So, therefore, the minimax problem is also a linear program, and it is not obvious at the first instance, but using a clever trick, all right, or by manipulating this, you can write the minimax problem as an equivalent linear program, and therefore, the linear program can be written in various forms and has very interesting applications. So, not only can be used to minimize the total transmit power, but it can also be used to, as I have said, it can also be used to minimize the maximum transmit power, maximum power transmitted by any of these base stations, thereby ensuring that this power burden or the transmitted power burden is fairly, or it's sort of evenly distributed on all the cooperating base stations, all right. So, that basically introduces the linear program and basically demonstrates its application in a practical scenario, in a practical wireless scenario for base station cooperation, all right. So, we will stop here and continue in the subsequent modules. Thank you very much.